Recall that a series is the sum of the terms of a sequence, and a partial sum, called S sub n, is the sum of the first n terms of the sequence. So here in this sequence we have 3, 5, 7, 9, 11, 13. So the partial sums are 3, 3 plus 5, 3 plus 5 plus 7, 3 plus 5 plus 7 plus 9, etc. An infinite sum would be the sum of all the terms in this infinite sequence. Most series do not have a defined infinite sum because the sum would be infinite. So one thing we might ask right now is, could an arithmetic series have an infinite sum? So think about if we're always adding or subtracting the same number between terms, notice that that sequence is just going to keep getting infinitely big, or in a positive direction, or infinitely big in the negative direction. So no, an arithmetic series cannot have an infinite sum. So the answer to that is no. But what if I want to find a more efficient way to add up the terms of an arithmetic sequence? What if I wanted to add up the first 50 terms? It wouldn't be very efficient to just list them and add them. But there is a way to do this. So to find the answer to this question, to make an efficient way, I want to tell you a historical story about a mathematician named Carl Friedrich Gauss. And so the story goes is that when little Carl Friedrich Gauss was in elementary school, maybe 7, 8, 9 years old, his teacher asked the students to add up the numbers from 1 to 100. He did that because perhaps he was frazzled and needed a little break, and he thought that would keep the kids occupied for a while. Who knows what the reason was. But little Carl Friedrich Gauss got the answer in just a matter of minutes. And here's what he did. He was a mathematical genius, by the way. So he noticed that when you add up the terms of a sequence, that there's a certain pattern that always occurs. Here's what he noticed. He noticed that 1 plus 100 is equal to, actually let me rewrite this a little bit, sorry. He noticed that 1 plus 100 is 101. He also noticed that 2 plus 99 is 101. And 3 plus 98 is 101, and 4 plus 97 is 101. And since there are 100 numbers, there are 50 pairs, and each pair is equal to 101. So there are 50 pairs of 101. So the sum is 5,050. Much faster than adding them up one at a time. So let's apply this little pattern that he noticed to our sequence that we have here. So 3 plus 5 plus 7 plus 9 plus 11 plus 13. Okay, so let's just do the first 6 terms and apply this little rule here. So notice that we add up the first and the last. This is 13. The second and the second and last, another 13, and the third plus a third. So we have 3 times 13 is 39. Okay, what about if we had an odd number of terms? How would this work out? So let's do just the first 5 terms. 3 plus 5 plus 7 plus 9 plus 11. So the first and last are add up to 14. The second and the second to the last add up to 14. And this is half of 14 in the middle. So what we have is 2.5 pairs, 2.5 times 14. And that turns out to be 35. Okay, so this pattern works no matter what arithmetic sequence we use. So we can say, in general, I'm going to extend this up again so I can write more easily on my smartboard. In general, we can take the first term plus the last term times the number, and I'll just put this in parentheses, times the number of pairs of terms. So this will always work for any arithmetic sequence. So let's think about how we would write this as a formula. So symbolically. So when I talk about writing as a formula, I'm just saying I'm going to take symbols and put them to the concept that we already see. All right, so we're seeing this pattern, we're going to put symbols to it. So we're going to say S sub n, the sum of the first n terms, is going to be n over 2. Okay, so n over 2 is the number of pairs of terms. And then the first plus the last term is a sub 1 plus a sub n. The first term plus the last term. Okay? Now, of course, we do need to know what a sub n is. So let's say we wanted to find out s sub 5. So this would be the sum of the first 5 terms, which is what we just did. So we would do 5 over 2, and then we would do 3 plus a sub 5. Well, we know that a sub 5 is 11, so we do 5 over 2 times 3 plus 11, and that would give us 2.5 times 14, which is just what we had before. All right, so let's apply this to the first 50 terms now. So s sub 50 is equal to 50 divided by 2, so we have 25 pairs of terms. The first term is 3, and the last term is the 50th term. Now, it's not 50, okay? So I want you to notice this is not 50, okay? It's not 50. It is the 50th term, okay? Not just the number 50. Now, the problem is, of course, I don't know the 50th term. Yet, we know how to find the 50th term. The 50th term in the sequence, which we'll call a sub 50, is just the first term plus the common difference added 49 times. Well, we can see that to get to each term, we add 2 each time. Well, to get to the 50th term, we're going to have to add 2 49 times. This is a sub 1 plus d times n minus 1. But it's easier just to remember the concept. I start with the first term and add 2 49 times to get to the 50th term. Well, this turns out to be 101. So now I know the number to put here. And so I can say the sum of the first 50 terms, s sub 50, is 25, 50 divided by 2, times 3 plus 101. And that turns out to be 2,600. And this is a much more efficient way to do it than, of course, adding up term after term after term. Now, just an interesting side note here is that if I were looking at the sequence of partial sums, 3, 8, 15, 24, and I look at the kind of sequence they make, this would be plus 5, plus 7, plus 9, plus 2, plus 2. You can see that this is a quadratic sequence. And this makes perfect sense because this rule is a quadratic rule. If I were to take right here n over 2 times a sub 1 plus a sub n, well, think about this. A sub n is a linear pattern. As a matter of fact, if we were to write the rule for a sub n, so let me kind of go down here. A sub n for this sequence, remember we're referring back to this sequence right up here, a sub n is going to be 3 plus n minus 1 times 2. Okay, so 3 plus or 2 times n minus 1, however you want to put it, or we could say 2n plus, and it would be 2n plus 1, because 2 times 1 is 2 plus 1 would be 3, so 2n plus 1. So the rule for this, a sub n is 2n plus 1. So if I look in general at what I'm writing here, for this particular sequence, a sub 1 is 3. So I would have s sub n is n over 2 times 3 plus 2n plus 1, because this right here is a sub n. All right, that part is a sub n. Now, if I simplify this, I would get n over 2 times 2n plus 4. That's not 24. It's supposed to be 2n plus 4. And then if I multiply this out, n over 2 times 2n would give me n squared. N over 2 times 4 would give me 2n. So n squared plus 2n. So S sub n is n squared plus 2n. This turns out to be a quadratic function. So the sum formula for an arithmetic sequence is quadratic. It's always going to turn out to be quadratic because there's going to be an n here and there's going to be an n in this part of the rule as well. That's just kind of a side note. It's not really important that you necessarily transfer this into looking like a quadratic equation or anything. The main thing I want you to remember is that you add the first term and the last term and then that sum times the number of pairs of terms. And in order to add the first term and the last term, sometimes you have to find the last term first.